Geographic information systems deal with two distinct image models. They are the vector model and the raster model. In the case of the raster model, of which this sheet of the military map of Portugal is an example, these are images made up of pixels, which correspond to a particular color. This type of image is generally appreciated as a whole, and when enlarged to pixel level, it tends to lose its meaning. They have some characteristics that are important in geographic information systems and even influence their performance. These include resolution, color coding, and recording format. For practical reasons, each of these characteristics will be dealt with separately, this being the first part relating to resolution. Concerning the resolution of raster images, take a look at the simple diagram shown here. This is a raster image with dimensions of 1 inch by 1 inch, or if you prefer 2.54 cm by 2.54 cm, which uses 4 by 4 pixels to represent its content. In other words, it has a resolution of 4 pixels per inch, which could be noted as 4 dpi or 4 dots per inch. It is therefore an image that in total is made up of 16 pixels. Another way of referring to image resolution, which is particularly important when it comes to geographic information systems, concerns the actual pixel size of the image, which means the area that is represented by each of these pixels. To understand this concept a little better, I propose a simple exercise. Let's start from the image we've visualized and export it at different resolutions. I'll start, for example, with the resolution proposed by ArcGIS Pro, 1965 by 1021 pixels, to cover the entire visualized image. Beforehand, I have no idea what the resolution of the resulting image will be, but we'll have a chance to check it out in a moment. Let's save it with a name that allows us to identify the image. Activate the creation of the georeferencing file. And upload the generated image. As you can see, this image allows you to clearly understand the content of the map. Its resolution, verified using an image editing program, is 120 dots per inch. Which corresponds to a resolution on the ground of 8.4 meters by 8.4 meters. As a general rule, pixels are square, so it is customary to refer only to the size of one of the sides. That means, adopting this rule, we would say that the spatial resolution of this image is 8.4 meters. For the next export, we're going to halve the number of pixels, both in width and height. 982 by 510 pixels. Loading the generated image shows a deterioration in image quality. For example, most of the town names are not legible and the houses and other smaller details are no longer represented intelligibly. The resolution of the image is 60 dots per inch, or half the resolution of the previous image, which makes perfect sense, since we have halved the number of pixels in each of its dimensions, while maintaining the total area to be exported. The resolution on the ground is 16.8 meters, which is twice the size of the previous image. Once again, this makes perfect sense. Since we have halved the number of pixels to represent the same area, the dimension represented by each pixel must double to represent the entire area. If you repeat the procedure, consecutively reducing the number of pixels in the image by half. That means 491 pixels by 255 pixels. And then to 246 pixels by 128 pixels. You will find that you get images with a marked degradation in visual quality. In line with the above reasoning, the resolutions of the images will be progressively half of the previous ones, that is, 30 dots per inch and 15 dots per inch, respectively. Similarly, their resolutions on the ground will be 33.6 meters. And 67.1 meters, respectively. In short, as the resolution of the image increases, the area represented by the pixel on the ground decreases. This leads to a progressively greater ability to represent smaller objects, which is why its spatial resolution is said to increase. For example, in an image with a spatial resolution of 2.5 meters, a square plot with 5 meters on its side would be represented by 4 pixels. On the other hand, in an image with a resolution of 10 meters, it would be represented together with other plots in its vicinity, and would not be able to be individualized in the resulting single pixel. Another interesting aspect concerns the file size of the images that have been created. As you can see, roughly speaking, the size of the images quadruples as we double the number of pixels in each of their dimensions. 84 kilobytes, 363 kilobytes, 1453 kilobytes, and 5360 kilobytes. In other words, increasing the resolution of images has the advantage of being able to represent smaller objects, but it also implies an increase in the volume of information to be stored on the disk, accompanied by an increase in the amount of information to be processed in the geographic information system and, consequently, an increase in the time it will take the system to carry out the analysis tasks requested of it. To finalize, concerning the map export operation we've just carried out, there are a few rules that can apply depending on the objectives. As a practical rule, if the image is to be viewed on a monitor or included in a presentation, I recommend a resolution of around 100 dots per inch. On the other hand, if the image is to be printed, a resolution of around 300 dots per inch is recommended. In reality, the resolution could be higher, reaching the printer's maximum resolution, but this increase is only justified if you use high-quality paper or other high-quality printing media, such as photographic paper. Using regular paper, a resolution of more than 300 dots per inch will not produce a substantially better image and, on the other hand, the file may be much larger. That's all for now. See you soon.